Well, thank you. I'm really pleased to be here, and I do realize that I'm the only thing standing between you and lunch. And I thank Terry for just doing a wonderful job of setting me up, introducing a lot of what I'm going to talk about. As somebody who's primarily a computer designer, I think it's just a really exciting time because AI has opened up a whole bunch of new possibilities. Unless you've been sleeping under a rock, you see AI everywhere. In the internet, it's enabling all sorts of things that weren't before possible. Now when you talk to your computer, it actually interprets your words correctly, as opposed to maybe 10 or 15 years ago when manually designed speech systems were not nearly as accurate. It's able to recognize things in images, tailor the ads that you see to your personal needs. In medicine and biology, it's revolutionizing interpretation of medical images, but also mining of data to do more accurate diagnoses, being able to interpret genomes and relate them to diseases and phenotypes. Media and entertainment, it's basically doing content creation, captioning, all sorts of things. Security and defense, it's great at detecting anomalies. You train it on what's normal and it can find out what's abnormal. And one thing at NVIDIA we're very excited about is we think that we can make a dent in the 1.3 million people who are killed on the highways every year by applying deep learning to autonomy in autonomous vehicles. Now, what's interesting about all of this technology, and it's a point that Terry made, is it's been enabled by hardware. When I was actually a graduate student in the 1980s, I studied his paper with Jeff Hinton on Boltzmann machines. I took a course by John Hopfield and built Hopfield networks and experimented with a lot of the technologies that were available at the time. And in fact, all of the technologies that we use in modern neural networks, well, almost all, there's some nuances, but deep neural networks, convolutional neural networks, stochastic gradient descent, backpropagation, all existed in the 1980s. So you may ask, why did it take until 2012 when Alex Krasinski and Jeff Hinton at Toronto built AlexNet, which basically won the ImageNet competition? Why did it take that 30-year period for it to come to fruition? And the answer is that two things were needed. You had the algorithms, that was 1/3 of the recipe. You also needed lots of data. We had that in the early 2000s. There were large labeled data sets available. Both ImageNet, which my colleague Fei-Fei Li at Stanford curated, as well as the Pascal data set and many others. But the real missing ingredient that came around in 2012 was computing engines fast enough to make it practical. With the fastest GPUs that my company NVIDIA made at the time, it still took 2 weeks to train ImageNet, to train, I jumped ahead there with the wrong button, to train AlexNet, which is the network shown here, on the ImageNet data set. But basically, once that computer horsepower was available, it was the spark that ignited the AI revolution. From that point forward, it's been applied to images, to speech recognition, to sequence analysis of text, to reinforcement learning to control robotics and many other things. And it's really taken off, and it's, what we've seen to date is the tip of the iceberg. AI is ultimately going to affect every aspect of how we work and live and play. It's really revolutionizing how we live. Now, what a lot of people don't appreciate is future progress in AI is gated by hardware. The AlexNet was great for ImageNet, but then there was tremendous progress made over the next several years, going to VGGNet and GoogleNet and ResNet. And if you look at that progress, just the model complexity increased by a factor of 16 over this 3-year period. And actually what's not shown in this is that it would have been a factor of 160 if it weren't for efficiency improvements that came in the jump from VGGNet to GoogleNet, where they basically separated the convolutions in space from the convolutions across the channels. On speech recognition, in just 1 year, Baidu going from Deep Speech 1 to Deep Speech 2, it took 10 times the compute horsepower to train the network. And in fact, when I talk to people at many of these companies that use our GPUs to train networks, they tell us that we'd like to run bigger networks, train them on more data, but we can't. We're limited by how fast the computers are that you're able to deliver to us. And so we feel a huge responsibility to continue to deliver faster computers because that's gating progress in AI. But there's a problem. Our two most recent Turing Award winners, my colleague John Hennessy at Stanford and Dave Patterson at Berkeley, in the latest edition of their textbook on computer architecture, published this figure, which basically shows that Moore's law is over. During a long period of time, we could count on getting more computer performance largely because of improvements in semiconductor technology. Over a good 20-year period from the mid-1980s to the mid-2000s, computers got faster at 50% per year. This was actually a combination of Moore's law, which gives us less expensive transistors, and what was called Dennard scaling, whereby scaling the supply voltage as we scaled the feature sizes, we basically got a factor of 3 improvement in performance per watt in every generation of semiconductor technology. Today, both Dennard scaling and Moore's law are over. We no longer get a substantial improvement in performance per watt by going to a finer geometry technology. It's certainly not the 3x we used to get. Going, for example, from 12 nanometers to 7 nanometers, we're seeing about a 20% improvement in performance per watt. And the transistors are actually getting more expensive. The 7 nanometer transistors on a per transistor basis cost more than the 12 nanometer transistors. So the challenge for us is, without semiconductor technology helping us very much, how can we continue to deliver improvements in performance? Let me give you just one example of how at NVIDIA we feel the need for this. So the movie I'm about to show shows a number of networks we collectively call DriveNet that are used in NVIDIA's drive platform, our self-driving car, which includes both hardware, the Drive Xavier and Drive Pegasus hardware platforms, but also a bunch of software and neural networks sitting on top of those platforms. We start out with a network that from visual can recognize both cars, you saw in the first one, but also free space. So we have 2 independent ways of saying where it's safe to drive. We can feed into our path planner a neural network that suggests the right path to follow. Then we put it all together. Here we're detecting objects, we're detecting free space, we're detecting lanes and suggesting paths. And we do this not for 1 camera, but for 12 cameras around the car, as well as 3 LiDARs and several radars. So if you look at what the computational requirements are of this, we can start by looking at the network we use for this, which is actually a variant of ResNet. We use ResNet 50, a 50-layer network, which is actually simpler than the network that won the ImageNet competition in 2015. But it's sort of the workhorse network for a lot of our computer vision tasks. And for ImageNet-sized images, it takes about 8 billion operations to process a single image in ResNet, to basically get out a detection or a classification or to find a path. But we're not processing 225 by 225 ImageNet images. Today, our self-driving car platform is doing HD images, 1920 by 1080, and shortly we'll be doing 4K images. But just even for the HD images, scaling it up, scaling this up to 30 frames per second is 230 gigaops, sort of quarter of a teraop for these thumbnails. And for HD images at 30 frames per second, it's almost 10 teraops. To put this in perspective, that's comparable to the performance of the Earth simulator, which was the fastest computer in the world in 2004. So how do we do this? Well, today we do this with GPUs. And to give you an idea of what the state of the art is, about 2 years ago we introduced the Volta V100. We actually consider kind of old technology today, but it is still the fastest tensor processing unit, the fastest computer specialized for deep learning. It's a huge die, 800 square millimeters with 21 billion transistors, but what gives it its performance are what we call tensor cores. We take our general, very programmable parallel computer, the GPU, and we put into it special purpose hardware tailored for the inner loop of deep learning. That inner loop is a matrix multiply. And by putting in special hardware dedicated for deep learning, we can essentially amortize out the overhead of that programmability and get efficiency comparable to the best that you could do if you build a chip only for deep learning, but retaining all of the generality of a completely programmable platform. It also has very high memory bandwidth because many deep learning tasks are memory bandwidth limited. And we put a very high bandwidth inter-GPU link on it, a technology we developed in NV Research called NVLink, that allows multiple GPUs to be ganged together and look to the programmer as a single GPU because they have essentially flat memory bandwidth. And today you can buy an NVIDIA DGX2, which is 16 of these V100s connected by a switch that we built called NV Switch, which appears as a giant GPU with 16 times this performance, which is very important to training large networks. Since announcing Volta about 2 years ago, this past summer we announced Turing, which comes in a couple different flavors. This is actually the same chip operating at different power levels. If you have a lot of power, the RTX 8000, it has roughly the same FP16 performance as Volta for training, But what's much more important is that for inference, where we tend to use int8 or int4 or even int1, it has support for int8 and int4 and int1 at proportionally higher rates. So it has a half a petaflop, or half a petaop, of int4 performance, which allows us to do very fast inference, very energy efficiently. And for many people who've told us they care more about hitting a particular power envelope, the 70-watt power envelope for certain data center servers, we basically take the same chip, we derate it, run it at a slower clock rate, lower voltage. We get about half the performance at a tiny fraction of about 1/4 of the power. And so this is currently what we sort of view as the universal solution to deep learning. You can do both training using the FP16 performance, and you can do inference with int8 or int4 performance. Now, what is this specialization and how does it work? Well, the tensor core is really a very simple thing. It's a matrix multiply accumulate unit. In fact, when we developed it, we didn't call it tensor core, we called it HMMA, half precision matrix multiply accumulate. It's an instruction we added to the GPU's instruction set and then built a hardware unit to implement that instruction. And what it does is it takes two 4x4 FP16 matrices and it multiplies them. So for example, it takes each row of the second matrix, multiplies it, dot products it with each column of the first matrix. You can see it sort of graphically here, and then sums those to get a third matrix, and then adds that third matrix to an existing matrix, usually at FP32 precision to avoid loss of accuracy, and that produces the result. Now this is 128 floating point operations, 64 multiplies, 64 adds. And what doing a lot of operations in a single instruction does is it amortizes overhead. The energy numbers I'm showing you here, I've scaled to 45 nanometers, so I'm not allowed to show you the actual numbers, but these are all proportionally correct, scaled from 12 to 45. In our Maxwell generation, the most complicated instruction we had was a half precision floating multiply accumulate. It did two operations, a 16-bit multiply, 16-bit add, consumed 1.5 picojoules doing those operations, but it takes 30 picojoules to fetch and decode the instruction and fetch the operands. So the overhead, the cost of programmability here, was 20x, 2,000%. In Pascal, we introduced a dot product instruction, half precision dot product 4. So it takes four 16-bit numbers, multiplies them by four 16-bit numbers, sums the result. It basically does one row by column of that matrix multiply. So we've improved the overhead. We're down to 5x of our energy and overhead. And then with Volta, with HMMA, we do 128 floating point operations. It's 110 picojoules. And the overhead now is just 27%. What that tells you is that if you threw everything else out of the GPU, no graphics, no programmability, all you built was the matrix multiply unit, much like the Google TPU, you would save 27%. Our judgment, having evaluated building a part like that, is that 27% is a very small price to pay for complete programmability and being able to use this thing for new algorithms that are being developed that need that flexibility and don't fit into a rigid single unit. I will say that the same GPU that provides this world-leading performance for deep learning training is also the core of the fastest supercomputer in the world. It's also the core of the fastest supercomputer in Europe, the fastest supercomputer in Japan, and 22 of the top 25 supercomputers in the Green 500 list for the most energy-efficient supercomputers in the world. So that's a generality of programmability. And this is actually very important for progress in science, because what people are discovering is that the right way to do science today is to apply machine learning to it, both to interpret the results. The Gordon Bell Prizes were awarded 2 weeks ago at supercomputing, and two of the finalists, in fact, the two that won, were both on this machine. One of them had a number of co-authors from NVIDIA, basically used deep learning to look at climate simulations and recognize important features, basically flows in the atmosphere and typhoons, that would otherwise be hard to manually recognize from the results of the climate simulations. And the other looked at ways of dealing with opioid addiction, also applying machine learning. And so what people are finding is that machine learning can be applied to science, both by running these scientific simulations and using deep learning to analyze the results, because it can discover things that humans would miss, And it also can actually accelerate the simulations themselves, since basically what you're doing with a deep network is you're learning a nonlinear function. You can learn a nonlinear function, which is the dynamics of the system that you're simulating. So rather than having to simulate it from first principles constituent equations, it's often much faster to do this by training a network to look at the existing state of the system and tell you what the future state of the system would be. And people get speedups of up to 100,000x, for example, using this for quantum chemistry to predict the state of systems and basically simulate Schrodinger's equation. Now, it's a case that in addition to putting GPUs in the data center for both training with either Volta or Turing and for inference with Turing, people want to put deep learning into embedded applications, into vehicles, into cameras, to basically create smart houses, smart cities, smart vehicles. And to do this, we actually build an embedded product called Xavier. Xavier is an AI supercomputer on a chip. It has a tenth of a Volta. It has 512 CUDA cores instead of the 5120 in Volta. And that gives you about 10 teraflops of FP16 performance. But it also has a deep learning accelerator that gives you another 20 teraops dedicated to doing neural networks. It has a number of specialized things for video, since processing images is very important. And we've put a lot of features in, including a number of redundancy and hardening against single event upsets and the like, so we can meet ASIL-C functional safety standards. And then when you use this in a duplex system with a checker, we can actually meet ASIL-D standards. And our Drive Pegasus system is designed to be ASIL-D, the highest level of reliability and what's required for level 4 and level 5 autonomy. What the core of this for deep learning is our NVDLA, the Deep Learning Accelerator. And I should say this is open sourced. You can go to nvdla.org and download the RTL, the hardware code for the Deep Learning Accelerator. You can also download all the software needed to support this. So we're trying to enable an ecosystem of people building embedded AI appliances. You know, we build our Xavier chip, but if it's not the right match for an embedded application, if you want to build a smart camera and a smart light bulb, you can download the DLA and run it. And it's very much like the Google TPU, and actually very much like our Tensor Core, that the core of it is a matrix multiply unit, a big array of multiply accumulate units. You know, we have 2,048 of them if you run int8 or 1,024 at int16 or FP16. But what makes it better than a Google TPU or most of the other accelerators I've investigated is we support two things that are really important for efficiency. The first is sparsity. Neural networks are sparse. They're not dense matrix multiplies. Typically, the weights are sparse. For fully connected layers, you can prune them down to about 10% density, and for convolutional layers to about 30%. And then for doing convolutions, as everybody remembers from their basic college courses, convolution, if you do it in the spatial domain, takes n squared operations for an m by n convolution. But if you do it in the frequency domain, it takes a single operation. You can do a pointwise multiply, and then basically do the inverse transform. And so we, rather than doing Fourier transforms, we do this with Winograd transforms, which are more efficient. But we have hardware support for Winograd transforms in the DLA, and hardware support for sparsity. So we can get much more efficiency than an accelerator that doesn't support either of those. Now, GPUs are an accelerator platform. And by that, what I mean is that what we do is we start out with a very general purpose programmable substrate, which includes a memory system, programmable processors that we call streaming multiprocessors, and that this is an ideal place to plug in special purpose units. We started out doing computer graphics, and we had special purpose units for rasterization, for texture filtering, for compositing. We moved on to doing scientific computing, and for us at the time, double precision floating point units were special purpose units for scientific computing. We went on to deep learning. We built tensor cores for both inference and training, and we bolted those on as special purpose units for deep learning. Most recently with Turing, we bolted on special purpose units for ray tracing. We call these RT cores. And what they do actually is that they traverse what's called a bounding volume hierarchy. If you're trying to render an image of this bunny and you're doing it by casting rays at the bunny, what you really want to do is you want to search for a needle in the haystack, this haystack of what's often billions of triangles, to find the first triangle that this ray hits. And the way you do that is you recursively subdivide space by dividing each cube into 8 subcubes at each level until you see which subcube your ray hits. You subdivide that into 8, see which subcube your ray hits, and you do this until you get down to a subcube that has a single triangle, and you see if your ray hits that triangle. And doing this in software is extremely computationally expensive. It's why doing ray trace images, the way most of the motion picture studios render feature animated films, typically takes hours per image. And so it's not real time. We like to go 60 frames per second, not one image per hour. Doing this has allowed us to do nearly real-time ray tracing by accelerating this process with an accelerator. In fact, our vision for the future of accelerated platforms, and the only way we're going to continue to deliver performance now that Moore's law is dead, is to take the applications of interest to us and accelerate them. But rather than having to build the whole computer system for each application, we realized that GPUs are a perfect substrate for this. They already have a very highly optimized memory system, and memories don't care whether the bits that they're holding represent triangles for ray tracing, activations and weights for deep learning, base pairs for genomics, whatever application you want to accelerate, that memory system is ideal for doing that. And actually designing that memory system, the interconnection network that supports it, the off-chip HBM DRAM is a very hard thing to do. So we can leverage that for many different applications. And simply, for a given application, if we identify a core function, a new tensor core, RT core-like thing that we want to do, we can take the piece of program that does that out, feed it through a high-level synthesis system, and build custom compute blocks that we then drop into our existing substrate. So for only the cost of doing these custom compute blocks, and in NVIDIA research, we're working on a number of tools to try to automate this process from running a program to having a compute block. We can basically have a new accelerator for a new application. So let me talk a little bit about how accelerators achieve their performance. We've already looked at one way they achieve their performance, which is that they reduce overhead. And I should point out that the overhead we were reducing on a GPU is actually quite a bit lower than on a CPU. And a typical, out-of-order CPU you might find in a data center like an Intel Xeon, if you're doing integer operations as you're doing for inference, and if you're using the CPU itself and not a vector extension, only about 0.1% of the energy is actually going into the payload, doing the integer operation. Typically, over 99.9% of the energy is going into instruction fetch, decode, reordering the instructions, renaming the registers, all of the things that make an out-of-order processor fast on single-thread performance gives you huge overhead. So we've talked about how to eliminate that by, first of all, using GPUs, which have much lower overhead because they're in-order and highly parallel machines, but also by building large operations like the tensor core operations, which do enough arithmetic operations that they amortize out the overhead. Let's talk about these other two things about reducing precision, exploiting parallelism. When you're choosing the number representation for doing a calculation, whether it be a scientific simulation or deep learning training, you really have two things you're worried about. One of them is dynamic range, and the other one is accuracy. What we've been able to show is that we have not been able to find a network that any customer has brought to us that we couldn't train with the dynamic range of FP16, which is about a 10 order of magnitude dynamic range. As long as we're willing to scale it per layer, and we've built automated software to do that scaling. In fact, the really critical scaling is that the dynamic range you have during the forward propagation, where you take, say, an image and you run it through the layers of a convolutional network, is very different from the dynamic range you have during back propagation, where you typically have very small gradients you're propagating back through the layers. But if you scale those differently, the dynamic range you have to worry about at any given time is small enough to be captured in that 10 orders of magnitude. And then for inference, what we have found is that int8 is sufficient for most inference applications. And it's really critical to reduce the precision you need for these operations for two reasons. The first is that when you look at the multiply accumulates, the cost of doing a multiply, and these are numbers from my colleague Mark Horowitz at Stanford from a 45 nanometer process, the cost of doing multiply is quadratic with the number of bits. So if I go from an 8-bit multiply, which is this line here, to a 32-bit multiply, it's not 4 times more expensive, it's 16 times more expensive. Because I'm producing an array of partial products where the number of partial products is a square of the number of bits in each operand. The other reason why it's really critical is because if you have large numbers, you have to store them and move them around. And storing them and moving them around is really expensive compared to actually doing the arithmetic. Well, you may think that a multiply is expensive. If I'm doing 8-bit multiplies, the cost of reading SRAM is an order of magnitude more expensive than doing that multiply. Even a small SRAM, an 8K SRAM right next to there. In fact, a rule of thumb I have is that every time you move up a level in the memory system, the cost of the access goes up by an order of magnitude. So reading that 8K SRAM sitting right next to your multiplier is 5 picojoules per word. Getting it globally on chip is 50 picojoules per word. And by the way, that's the same 5 picojoules to reference the SRAM. You build big SRAM arrays out of many little SRAM arrays. So you're actually referencing an 8K SRAM here at 5 picojoules, and you're spending the other 45 picojoules moving data. That's basically driving wires from where the SRAM array is to where you're consuming the result. And heaven forbid you have to go off chip, even with an LPDDR DRAM that's used for mobile products. It's about the lowest energy per bit DRAM you can get. It's still another order of magnitude more expensive to go off chip. So you have to avoid going off chip at all costs. Now, one way of making things even smaller than the 8-bit inference is to basically use deep learning to do basically non-uniform quantization. Suppose I decide I want to use 4 bits to represent the weights of a neural network. After pruning, which I'll talk about in a little while, the distribution of weights is shown here in blue. This is the probability distribution function, probability density function of these weights. And if I use uniform quantization, say an integer representation, and I have 4 bits, I'll get 16 evenly spaced symbols, which are shown by the green X's here. But you can see that that's highly inefficient. I have a lot of symbols out here where nothing interesting is happening, and where all the interesting stuff is happening, I'm sampling it very coarsely. So a much more efficient way of doing business is to basically do what's done by the red dots here, is to use a code book to sample where the interesting things are happening. So I sample very densely where the lobes of this distribution are, and I put only a few samples out in the outer reaches where it's not very important. And what's really interesting is that you can use the same algorithms we use to train our networks to train this code book. Anything you can differentiate, you can train with stochastic gradient descent. We can differentiate into this code book and take the partial derivative of the loss function with respect to the code words, and then use that to train the code words to find the optimal set of code words for a given function. This is work that was done by my former PhD student, Song Han, and I, published at iClear a couple years ago, and Song is now on the faculty at MIT. And what he showed is that if you take this technique for fully connected layers, you can get by with 4 bits of resolution and have absolutely no loss of accuracy. And you don't get catastrophic loss of accuracy until you drop below 2 bits of accuracy. For convolutional layers, those numbers are 6 and 4. There's no loss of accuracy to 6 bits, where typically you would have needed 8, and you don't get catastrophic loss until you get down to 4 bits. So that's one way of reducing things, is to come up with very dense encodings. First of all, to use low precision numbers, and then where appropriate, to actually further encode by using non-uniform quantization. The other thing that we realized, this is also work that I did with Song that was published in NIPS in 2015, is that you don't need most of the connections. If you look at the brain's connectivity, it is very sparse. In fact, it starts out denser and gets sparser. We have the most neurons that we ever have when we're about 1 year old. And then our brains prune themselves and reduce the neurons and keep the useful ones and get rid of the non-useful ones. We can do the same thing with the connections here. In fact, what we do is we take a neural network and we train it dense, and then we basically lop out the lowest weight neurons. And when we first did this, we had horrible accuracy. And then we realized that the missing ingredient was to retrain holding that sparsity constraint. And when we did that, what we found was the following. So we started out with a certain level of accuracy. So this is relative accuracy to the original network. And this, I believe, was results on VGGNet. And when we pruned it without retraining, we got the purple line here, which basically said if you took more than half the weights out, you started to lose accuracy, and you'd have really awful accuracy as you got sparser. But if you retrained, which is the green line here, you actually got better accuracy for a while, and you didn't lose accuracy until you got out nearly 90%. And then anything worth doing once is worth repeating. So if you do that iteratively, you get the red line, and you can basically take 90% of the weights out. You can throw 9/10 of the weights out and lose no accuracy. Now, it turns out that especially if you use what's called a ReLU or rectified linear unit nonlinearity in your network, you actually have also many zeros in the activations, because all the negative numbers turn into zeros. And we found only about 30% of the activations were non-zero. So of all the multiplies you're doing for the neural network for a fully connected layer, only 3% of them have to be done. The other ones all have a zero in either the weight or the activation. And that's a huge advantage. So a lot of these things are grist for building accelerators. One of the first accelerators I built with my students at Stanford was called the Efficient Inference Engine. And what it was doing was showing that you could efficiently exploit sparsity at this level of 10 to 30% dense. If you talk to a numerical analyst, what they'll explain to you is that it's not worth using the sparse matrix package until your sparsity gets down to well under your density is well under 1%, because the overhead of walking the pointers and doing all the irregular access swamps that. But if you can build special purpose hardware, I can walk the pointers for free. Building some addressing to walk the pointer structure is very inexpensive to do. We can also compress the pointer structure, so having to keep 32 or 64 bits per pointer as in a conventional sparse matrix package, we can run length encode them at 4 bits per pointer, so the overhead of storing those pointers becomes negligible, and we expand them through this accumulation process. Because we're doing train quantization, we basically have a code book that would be very expensive to do in software, is absolutely dirt cheap to do in hardware, and we can basically get all of the advantage of sparsity and compression with essentially no overhead by using special purpose hardware to take the hard parts out of that. To show you that it's basically all about the memory, the green area here is storing payload data. That's actually storing the non-zero elements of the sparse matrix. The sparse matrix pointer structures are shown here on either side, and the logic is this little stuff in the middle. The logic almost doesn't matter, either in terms of area or power. It's all dominated by memory. We also went on, this is with part of my research group at NVIDIA, to look at how to do sparse convolutions most efficiently. And so it turns out here I have a sparse activation layer shown here in green. I want to convolve it with a sparse kernel of weights in a 3x3 convolution, and that will actually fill in the output activations until I apply the ReLU function after summing everything up. And the way we chose to do this actually is to observe that every one of these weights has to be multiplied, or excuse me, every one of these activations has to be multiplied by every one of these weights. So we just go ahead and do that. We build we fetch the weights W at a time, we fetch the activations M at a time, we build a big M times W multiplier array, we multiply every weight by every multiplier, and then we sort out where they want to go. And it turns out if you take the X and Y coordinates of these, you add them together, that gives you the X and Y coordinate of the output activation they need to be summed into. And so we use an operation that I actually wrote a paper about in supercomputing in 2005 called scatter-add, and build a scatter-add unit to basically sort all those output activations out. The energy efficiency here for SCNN winds up being about 3x over doing the dense computation when you have about a 30% density of weight. So it's achieving very good efficiency in exploiting sparsity. Now it turns out this is actually from an accelerator that we haven't talked a lot about yet, so I can't give you the details of this accelerator, but if you start looking at some of the best ways we know of building accelerators, they start to be dominated not by the arithmetic, but by moving data around, by memory access, and a lot of memory access is actually moving data. To give you some numbers, the real figure of merit for doing inference, actually for doing training as well, I think of as femtojoules per Mac. And that's not just measuring the femtojoules of the arithmetic unit. That's a relatively easy thing to get down. It's the femtojoules of everything divided by the number of Macs. And for our NVDLA, which is about the most efficient unit I've seen to date, that number is 200 femtojoules per Mac. The number here with full voltage scaling is on this axis. This is the femtojoules per Mac axis. And you see we're right around 80. There's actually some slightly newer results we have from this accelerator where it's around 70. And I'm actually quite confident that we can get it under 50 femtojoules per Mac. But part of what we have to do to get down there is to realize at this point we've reduced the arithmetic, which are these two blue areas, to under 20 with aggressive voltage scaling. And the SRAM axes, the weight buffer and the activation buffer, which are these green areas, are starting to dominate everything. And that basically says we have to really worry a lot about how we access memory, make memory access very efficient, and to make data movement very efficient. And so, for example, one project I started in NVIDIA research was to look at how to improve the efficiency of data movement by a factor of 4. And it's basically by using every electron twice. This is a paper we published in ISSCC in 2016. We start out by starting with an electron at VDD. We use that electron to drive one signal on this upper tier. Then we get down to a V mid, so if we're running at a 1 volt supply, this is at a half a volt. And then we use that same electron to drive another bit. And it turns out that because energy is CV squared, this is a quarter the energy of sending the bits. And we basically achieve this with no loss of performance. So So let me flip the coin around here a little bit, and something that's very important to me as we develop better GPUs, better accelerators for deep learning, is it's important for us to eat our own dog food. So we actually do a lot of deep learning research at NVIDIA Research as well. I'm going to go through this quickly because I see the countdown to lunch going on here. We do a lot on perception. We currently have the state-of-the-art in semantic segmentation, the best optical flow neural network. And I encourage you to read this CVPR paper because this is a great example of how, rather than throwing away computer vision research of the last 20 years, we took the best computer vision research for optical flow, and then we applied machine learning to make it better. So it actually combines the best of both worlds to get results that are better than the people who've tried to do end-to-end deep learning to learn optical flow. We very often have 3D data, so if we have a LiDAR, we can do semantic point cloud segmentation from LiDAR data. Because we are still a graphics company, we spend a lot of time applying deep learning to graphics, both for content creation. A lot of people don't appreciate it, but the gaming industry is bigger than the motion picture industry in terms of dollar revenue per year. Perhaps if they held Oscars, it would get more attention. And a big thing, the big limiter there is artist time. They spend a lot of time basically manipulating what are called rigs with typically 300 control points to basically animate faces. We were able to apply deep learning to take an audio stream and manipulate the faces. We also apply it to classic graphics problems like denoising, anti-aliasing, and scheduling where to cast the rays in ray tracing. A really important feature here is in the denoising. To produce a motion picture quality image with ray tracing takes about 10,000 rays per pixel. If you're doing that at 4K, where you now have something like 8 million pixels, the number of rays you have to cast is enormous, and it winds up taking an hour to cast an image. The image at the left is 5 rays per pixel. You see, it's very grainy. It's like you would get if you set your camera to very high ISO. The image at the right is that same image after passing it through a neural network that denoises it. And this technology has enabled us to, with our RT cores in Turing, ship a product that for professional graphics can do ray tracing that is absolutely as good as the best motion pictures at about 5 frames per second. It's not good enough for real-time graphics yet, which requires 60. We actually, for real-time graphics, use the ray tracing for shadows and reflections, but we can do complete physically based rendering with path tracing for professional graphics at things that architects and automotive designers find very acceptable frame rates. Now, I have to say that Terry really set me up for this. So the progressive GAN work he talked about is a product of NVIDIA Research, our research group in Helsinki, Finland. And the problem they addressed was that training a GAN, a generative adversarial network, where I basically feed a random variable into a generator, it produces an image, and I have a discriminator network that basically just says real or fake. And you have to realize that the generator network has never seen an image. It simply tries things and tries to fool the discriminator, and you're training them both at the same time. But the problem we found, being in graphics and wanting to do high-resolution images, is it was very hard to generate a high-resolution image because you had too many unbound variables you were trying to learn all at the same time. And it would basically get stuck, it would not converge, and things would be really awful. You'd produce awful images. GANs are a wonderful technology invented by Ian Goodfellow when he was at Toronto, a student of Jeff Hinton's. But they required a lot of careful care and feeding. What we realized that this was basically trying to teach the network differential geometry before it mastered basic arithmetic. And just like a student that you're trying to teach math to, what you do is you start simple. What you would do is you would start saying, okay, let's start with adding. We'll teach you how to add numbers. And then we'll move on to multiplication, and later on maybe basic calculus. So the first place we start is with 4x4 images. We feed the random number in, we produce a 4x4 image, and this basically trains both the generator and the discriminator on an easy problem. When they get the easy problem right, we go up to 8x8. When they get that right, we go up to higher resolution and so forth. And here's the movie of training this. This shows the resolution that we're currently training at, the amount of training time. And by mastering each level of resolution before moving to the next, we were able to be the first to generate high-resolution images that actually look really good. Let me move on. It also says that you can now take that random number that's feeding into the network and sweep it around, and you can sort of continuously vary from one image to the next. There are people now who are able to separate those latent factors into different terms. So you can have hair color be one, gender be one, facial hair be one, and sweep those variables independently and get these. So let me wrap up and try to keep us on time into lunch. It's a really exciting time to be building computers because the whole application area is changing. Deep learning is fueling a revolution in AI that's affecting every aspect of our lives. And this revolution has been enabled by hardware. All of the algorithms have been around since the 1980s. It wasn't until we had, in 2012, we had GPUs with enough horsepower to run them on a reasonable data set in a reasonable amount of time that we really ignited the spark that set off the deep learning revolution. And today, that deep learning revolution is being paced by hardware as we go to more complex models with larger data sets that quadratically increases the amount of computation that we need to use to train those models, and we need more powerful computers to train them in an environment where Moore's law is dead. We're not getting any more performance out of semiconductor technology. And so our solution for this is accelerators. And GPUs provide the underlying platform, the base memory system, the programmable core operations into which we can plug in special purpose accelerators, our tensor cores, our ray tracing cores, double precision floating point for scientific computing. And these are currently the most efficient both training platforms and inference platforms, even compared against dedicated TPUs that only do one function. Our total number of ops per chip and our ops per watt are both better. The one way of achieving improved performance is to basically do less work. One of my favorite mottos is never put off till tomorrow what you can put off forever. Right? So rather than doing a 32-bit floating point operation, we can do an 8-bit integer operation or even use 1 to 6 bits to represent weights. And we can throw away most of the weights and most of the activations are 0, so that most of the multiplies don't have to be done by exploiting sparsity. And by building accelerators that can basically handle sparsity, the irregularity of sparsity very efficiently, and handle low precision encoded numbers very efficiently, we can get the gains of that, which we couldn't get if we tried to implement that in software. And then to basically continue driving ourselves to do better, we are our own biggest customers of this technology for our autonomous vehicles that I showed you the movie about earlier, for computer graphics, for perception, for image synthesis. So thank you very much. I'd be happy to take questions if there's time.
Thank you. Thank you very much for your wonderful presentation. Would like to invite Charles Esabak. Thank you very much.